Still didn't record it. That's okay. Okay. Most of you are probably using statics habits to solve this problem, okay? And a lot of statics habits are just kind of shortcut tricks that
Direction of
like
its
that's
motion.
what's really
The
going on
compass
with
of
this
constant
work.
acceleration.
Okay.
Okay.
And that's exactly what an engineer might want to do. Okay, you bypass actually thinking through and you apply the tools and the tricks so that what you build works. Okay, what you design works. Okay, in physics, we want to go to the basic principles behind all that because then you better understand why those tricks work. Okay, so the foundations here, you did assignments with vectors. I don't know how you solved them. If you solve them using statics tricks, again, you kind of bypassed what you really need to know about vectors and the way you really need to conceive them. Now, the fact that the majority of the classes had linear algebra, this should also kind of click with the linear algebra, which is all about vectors. Less about force vectors than abstract vectors. Okay, so the way I'm going to do this is, first of all, I'm going to use different colors here. Okay, so I'm going to say, okay, I've got a force F1 in this direction and a force F2 in this direction. Okay. Now, that isn't a real good diagram because this rubber band you can even see is longer than this one, and they have the same force rule. So if you have a greater length, it's going to give you a greater force. And of course, that's intuitive anyway, if they're equivalent rubber bands, which they aren't necessarily, but we're assuming they are. Okay. So they both have the same force characteristic, which is this. Okay, well, we also have two length vectors. Okay, and I'm going to call those L1 and L2. So now I can carefully label what I'm doing rather than a series of pictures like you would. I mean, the pictures are great, the triangles and everything that I've seen most of you drawing. But let's do it in a more compact notation that allows you to really specify whatever everything is. Okay, so L1 equals 3i plus 4j. Get used to the I and j vectors. Majority of the class has multivariable calculus coming up. You want to get used to these things now. Okay. They're not hard. You just got to think in terms of these vectors rather than statics pictures. Okay. Or in addition to your statics pictures are fine, but make sense of it by writing your vectors out algebraically. Okay. L1 is 3i plus 4j. L1 is the length of the L1 vector. Length is 5. Okay. Question? Hang on. Okay, talk about being precise and everything. I'm not having a great morning with being precise. So keep an eye on it. It's on 4i and 3j. And you do want to get it right because right now it's not going to make a difference in finding the magnitude of the force. But later on, when we find the unit vector, it's going to make a big difference. Okay, I'm not going to bother changing 4 and 3 there, but I usually write it the same order. Okay, L2 equals -7i plus 3j. Okay, now do these vectors make sense? Let's see. -7i plus 3j would be into the second quadrant, and that's aimed at the second quadrant. I mean, and 4i plus 3j, yeah, that's in the right direction. Okay, so that checks out with the picture. The magnitude of L2, well, that's L2. Felt like 7.6. About what you got? You don't say anything, just say if it's within a tenth, it's okay. Okay, it's a little over 7. Okay, 7 units in this direction, 3 units in this direction. This vector isn't much longer than a vector of length 7, which would be like here, right? X component of that vector has magnitude 7. If you draw the triangle, the y component isn't that big. The y component therefore won't add all that much to the magnitude of the x component. And you want to have that intuition. Statics for physics for anything. Try to think through those ideas as you work these problems. Okay. So unit vectors. If you have to remember a formula to calculate a unit vector, you don't understand unit vectors. And nobody really used unit vectors. Okay. So we had everything you needed to get the unit vector. Well, what's the idea of a unit vector? If you take the length of a vector and want to get a vector in the same direction with twice the length, what do? You multiply it by 2, right? And you still have the same direction because your components are still in the same proportion. The rise over run is still going to be the same. Okay, the angle of the vector is still going to be the same because you're just multiplying it by positive number. If you multiply it by negative number, of course, then it goes in the opposite direction, still along the same line, but you change the direction. Okay, well, if you want to get a vector of length 12, if you have a vector of length 9, and you want to get a vector of length 1 in the same direction, are you going to multiply 9 by some positive number, or some number bigger than 1, or are you going to divide it by number? Say multiply, divide. You're going to divide. You got to make it short. So you're going to divide its length. Gets back to the meaning of division, which a lot of people, you don't have a problem for y'all, a lot of people come out of our school systems, and it's a national curriculum, it's not just here. Not really understanding what division means. If you divide something, if you divide a length, you get a shorter length. If you divide it by length, a number bigger than 1, right? People don't understand that. They just plug it into a calculator and take what it gets. Okay, well, there are analogies. It's easy to plug things into a calculator, take what they get. And if you're following the rules really well, you're going to get the right answer, but you're really going to understand what you just did. Okay, that's as far as divided by a number, yeah, you are. Okay, there are other things where you really want to think about what it all means and think more deeply. Keep learning to think more deeply. It makes a better problem solver. Okay. Okay, so anyhow, if you didn't understand that you divide the vector by its length, okay, so you got a vector of length 9 and divide it by 9, You're gonna have vector length 1, and that's what a unit vector is. 1 is your unit, okay? Get that straight. Unit vectors are all over the place. And you really have to be able to use them. They did it in linear algebra, but there's a rule that says you do this. So you probably follow that rule without thinking deeply about it. Okay. And y'all did well. Everybody took linear algebra quite well. I want to think in terms of what these things are. It'll become more clear in multivariable calculus for those who take. Okay. And the engineering students need to do that. Others manage to escape them. Okay. Now, you divide L1 by this. So L1 is now it's natural that you want to find the angles of these things and use your sines and cosines. That just confuses the issue. Again, that's a habit you're going to have if you're doing a lot of that, which you are doing in statics, okay? But it's not necessary here, and it saves you some work if you just divide these components by 7.6. And that's going to give you approximately, okay, if it was 7, then you'd have 0.6. But it's going to be less than that. And actually, I know what it's going to be. Especially since 7.6 is the latest length that I calculated, not the one that goes with this vector. Okay, it's over 5. I was looking for 0.8 and 0.6 in that calculation, and I wasn't finding it. Well, there's your unit vector. Okay, well, let's calculate the force. 3 newtons per centimeter multiplied by the length, which is 5 centimeters, minus 3 centimeters, which is 3 newtons per centimeter times 2 centimeters, which is 6 newtons. Write out all your units. Make sure centimeters are divided by centimeters, and 3 newtons is multiplied by 2 gives you newtons. That's why I wrote the newton over centimeter there. This would not have been a correct formula if I hadn't had the units. And I keep emphasizing it's important to use units. Either check your dimensions out rigorously, you do your dimensional analysis, or put units into your calculations. Preferably both at this stage. Then when you get really confident with your dimensional analysis, what it always matches what you get when you put the units into the equations. You get away with the engineering trick of never writing units down for anything. So you crash your spacecraft into Mars. Okay. I told you about that, right? Yeah, sure. I done that recently and thought I was seeing your faces when I did it. Okay. Okay, so anyhow, you get this. Now, just for quick practice, quickly. Go ahead and use what we got about the length of L2, or use your own number for L2, doesn't matter. But write things down with this notation in this format and come out with your L2. Oh, wait, so F1 is then 6 newtons multiplied by something very close to 0.8I plus 6J, and this equals 4.85 plus 3.6J. Imitate everything I've done here, 3-second rubber band, and then see what the sum of your forces is. Okay, again, you need to be careful that you understand every step that you're doing. For example, at least one person multiplied their magnitude of their second force is like 13.8 newtons or something like that. By the L2 vector. Okay. And the problem with that, what we need to understand is if you want to get the force is going to have a magnitude of 13.8 newtons. This force would have a magnitude of 13.8 newtons multiplied by the magnitude of this vector. It wouldn't have a magnitude of 13.8 newtons, and it would be way too big. Okay. Now you could do this over your 7.6, and this would now be a unit vector, right? So that would be a perfectly good step, but you have to make sure the concept is you're going to change the magnitude of the force if you multiply it by any vector that isn't a unit vector. So you want to be sure you totally understand that. Okay. And then you get this, and you get something like very roughly 11 newtons times I plus 5 newtons times J. And I'm not even trying to calculate those, so we just kind of two of estimates. 7 over 10, and it's negative 11. 7 over 7.6 is pretty close to 1. So it's not going to be that much less than 13.8 newtons. Okay. Probably actually closer to 12 newtons than 11, so we change that. And then 3 divided by 7.6, 3.8 divided by 7.6 would be half. It's somewhat less than half. I think I underestimated that one too. And I can check that now. What's the magnitude of this vector? If I square 12, I get 144. I square 5, I get 25. Okay. 144 and 25 is 169 squared, and that's 13. So this vector has a magnitude of 13 newtons, not 13.8 newtons. So I'm going to promote that to 6 newtons. Now, you don't want to do it by estimate and trial and error and guess and check. You just punch it into your calculator at that point. Okay. And at least one person did just use 7 over 7.6 and 3 over 3.7.6, and then just punch it into the calculator. That's fine because you're assured that that was a unit vector. You can look at it and see, yeah, and make sure that was a unit vector. Okay, well, now we have this. So what are we going to do with it? We're going to add these two forces. So what's the sum of these two forces? Just using what we have on the board, and not static strips with triangles and law of cosines and everything else, which you might not have used at this point, but yeah, they're very relevant. Okay, but it's much simpler if we just keep it here. Now, again, there's good reason to use law of cosines in some of those situations. So we don't really run into situations in this course where we use anything but just vectors with components and right angle trigonometry. Makes the trig much simpler. And conceptually, it's going to accomplish what we want to accomplish with this. Now, to be consistent down here, I did the 4.8, 3.6, I didn't write my units down. So I'm gonna fix that, okay? It's real easy to do because you're focused on the numbers. You really have to, at the end, think through all the units, and kind of fill them in if you miss them. Or do the dimensional analysis at the beginning. Get what everything means while you're working the numbers. At some point, gotta get the numbers right, so that can be another thing to do. And then it's that's just suppressing obvious units. It's negative 12i. This is approximate, using my approximation. It's going to be negative 7.2i plus 9.6j. Okay. So you've got to get some slightly different numbers. There it is. Now, obviously you want pictures. So now that you've done the formal calculation, remind yourself of what you did. Okay, what you did was you took force one. My picture, I need to think color. The F1 was only a force of magnitude 6 newtons. F2 had almost twice the magnitude. Now, the rubber band didn't have twice the length. But when you run through this, it's a length in excess of 3 centimeters, because the rubber band doesn't exert any force until you start stretching it. Assuming rubber band that starts out with a length of 3 centimeters and a linear force, which isn't quite right for rubber band, but it's actually close enough that we do a lot of good things with it. Okay. So you've got this picture of this force. With components, I want to draw the components shortly. And whoops, wait a minute. And force is supposed to be a curved force. Be too ridiculous. Compensate for the fact I'm making a lot of mistakes today. Okay. So now we got a vector. It's not twice as long. Text is over. And I still use the wrong name color. Make it look at this coefficient. Okay, here's your F1. Here's your F2. Now we have components. And components here are 3.6 newtons and 4.8 newtons. Components here are approximately negative 12 newtons. I drew this thing way too steep. And 6 newtons. So the picture isn't very good. This thing should have been in a much different angle. Still, when we add these things up, we see that 3.6 newtons and the negative 12 newtons is a result of negative 7.2 newtons. Okay. 3.6 this way, 12 that way gives us 7.2 that way. Up here, these reinforced 4.8 and 6 give us I've explained it, I'm gonna redraw it. Anybody wrong with that picture? Okay. So we got this one and this one, just roughly twice as long. Draw the angle a little better. So here's our F1. Here's our F2. And now we've got 4.8 newtons in this direction, not 3.6. And 3.6 newtons in this direction, not 4.8. And over here, we've got about negative 12 newtons and about 6 newtons. Okay. Okay, what I'm going to do is I'm going to come to a set of coordinate axes. I'm going to represent all these functions by their components. I just pull the components out of the picture because they all fit the picture. The angles look about right for change. The numbers are actually right this time because I was more careful. So I put these together. Well, put these vectors together head to tail. I go out this far and then I come back this far. So I end up with the equivalent negative 7.2 newtons this way, 9.6 newtons this way, giving me my ultimate goal. Should have labeled these on the other side. This one's going to work either way. But my resultant force. I'll use F total represent this force. And that equals, well, we know what it equals, we calculated it. This. Okay, well, I'll calculate the angle and magnitude of that force. Actually, before we do that, we get the angle and magnitude. That's very straightforward. It's just stare in theorem, the arctangent, and make sure you're in the right quadrant. What's the equivalent? Write it down for me. So what's the equivalent? the negative of F2, right, of F total. Okay, now you text probably calls out the resultant, and that's what we usually call it. But call it the total force, so we don't. So we keep the terminology as basic as possible, but that is the resultant, and that's what we're going to use in the future. Okay. So I'll just write this as a result. Let's equal out to the result. Okay. That's an intuitive answer, and it's absolutely right. But there's some advantage in doing this on more formal calculation. Okay. So I'll do F sub EQ for equilibrium. It's the force with the property that the sum of the existing forces and the equilibrium gives you the zero force. Okay. And that's going to imply if you got zero force, you got zero acceleration. Okay. So if the thing is initially stationary, it stays stationary. Now, if it's initially moving, it remains moving. That same speed and direction. So for example, if we set this up on a table and then put the table in wheels and roll it down the hall, it's still in equilibrium. Okay, because as long as we roll it without accelerating, okay, we roll it at a constant speed, no acceleration, then there's still zero acceleration, and this still works. Okay. If there is an acceleration, then it's going to stretch these rubber bands unequally. If we accelerate in this direction, it's going to cause the horizontal components of these forces to change a bit. Okay, we'll worry about that later. It's a little bit complicated. Not too bad. Okay. But we'd be in a non-inertial, what's called a non-inertial reference frame. And that's an important concept in the chapter you're working on. So you heard it here first if you haven't already heard it. Okay. So when you see it, maybe it'll remind you of the situation. Okay, well, the algebra of this is this, right? And then just write out the components. Of course, you're going to end up with the same thing. Sometimes you want an equation. And sometimes you want to separate your forces into two columns, the X force and the Y force. You have two columns and you add them up and everything comes out and you're going to see that. This is what's going on. Okay. So my last question is, what's the magnitude and angle of this force? And I think you already know this. So And I'm not always consistent with my absolute value or magnitude signs. It's a magnitude of this, and that's going to be the square root of. Okay. And if you square 7.2, you get about 54, 53, 54, square 9.6, you get about 92. That's what it is. Okay, now you can easily work it out yourself. And then on a picture, you're probably going to want to do a measure from the x-axis. You're going to take the inverse tangent of y component over the x component. And the magnitude of the inverse tangent. If you're out of the way. And I'm writing the negative sign in there. Because ultimately, you're gonna probably do, if you're doing a lot of calculations of this nature, you're gonna do them in a computer. And you'll enter them into a computer. If you enter like an Excel or into a computer, you're gonna want this IJ notation because you can't enter your statics pictures into a computer. Now, of course, as an engineer, you'll have all kinds of tools that'll take care of all that for you. But you want to think it through now, so you know if you've applied the tool right and get something that makes sense. Okay, well, anyhow, you get this, and that's going to be something like, I'm just guessing, going to be less 30 degrees, 36 degrees. Now, with your numbers, you get a slightly different result. But you can then figure out total as a vector, and you can think of this vector. The length, well, at 36 degrees. And this reconciles all the vector calculations and all the pictures. Okay. And you want to have those reconciled. You want that in a neat, nice, tight little bundle because you're going to do a number of calculations of this nature. And if you do them by shortcuts, you're not going to end up understanding it as well. Now, do it this way and do it by shortcuts, at least a few problems. So you see how the shortcuts and everything fit the same picture that we really going to use here. Okay. Not just about getting the right answer, although in engineering, that's the really important thing, even more important than in physics, but understanding the process so you understand the physics of what's going on. Yeah, but it doesn't matter if it's moving or not, the magnet doesn't care. Right there at that position now, which is the direction of the force, basically. So all you do is just show me the direction. Force on the ball.
This is on the table.
Well,
Okay.
so yeah, assume it's moving in a plane. It's off the end of the ramp, so you don't have to worry about a Z direction. Well, if you want to worry about the Z direction, just give me a good three-dimensional adaptation. I'll be even more than happy. Okay. Reasonable. So. Take a look here. Here we got the ball, here we got the magnet, right? What's the ball going to do? So what was the direction of the force of the ball? For the magnet, right? Okay.
She doesn't shake it, she just goes.
Okay, I'm not sure I don't know what. I got lost track of the recording. Unfortunately, nobody else screamed and identified themselves, so okay. Okay. But if the magnet's here and the ball's here and it's in a plane, what's going to happen? The ball's going to go toward the magnet. You go a straight line toward the magnet, pretty much. Now, the magnet's not a point source, so forth, so that's not totally correct, but intuitively. Force about the magnet. Okay. And of course, when the ball here, up here, the force is going to be wherever the ball is, the force is toward the magnet, right? Ball being sped up by the magnet or slowed down. How many think it's being sped up? How many think it's been slowed down? How many think you give it up, down, or leave it? Okay, we have disagreements. Okay. Well, let's look at what this picture is telling us. First thing is we have forces. I've chosen the X and Y directions to be in the direction of motion of the ball. Well, the natural thing to do when you have a force is then on a coordinate system, you break it into components, right? Okay. What's this component doing? You had a force in this direction on the ball, which you do, in addition to force in this direction. What's this force doing? It's speeding up the ball, isn't it? So the ball's being sped up. So this component really can't read that. It's too small, I'm not even sure it's going to come out on the video, but it's a in direction of motion, speed up ball. I didn't even have the room to write an S in speed. So speed up ball, you get the message, but it's not quite dramatic. Okay. So ball's going to speed up a little. What happens here? It's perpendicular. To the direction of motion, has no effect on speed, but it changes direction. Changes direction, not speed. Well, that's important. So what's going to happen to this thing? Well, you know that somehow the path curves in response to all these forces. Okay, well, when the ball's over here, what's happening? Well, the speed's gonna be changed. And it's a little closer to the magnet, maybe, maybe not. So maybe you get even more force back in this direction. So maybe slows the ball down a little bit. Okay, now the ball's moving pretty fast. There's not that much change in speed or direction. But all that's going on, okay? And wherever the ball makes its closest approach to the magnet, well, it's a little more complicated. Because when we get out here, the magnet's not exerting much force at all. Because magnet force, magnetic fields like in this direction, that gets complicated, we're not gonna worry about it. Just an intuitive idea. And magnet forces are complicated, so we're not gonna use them. In statics type situations. I don't know, we might. It would be kind of fun, but we're not gonna analyze it. Okay. Except maybe to determine, well, this must have been the direction because it equilibrated these other forces. Okay. Quickly, we want to think about the other situation where we have the balance with the magnet sitting on it. The stack of dominoes. I'm just going to write as a little set of dotted lines, as the dominoes are pretty much invisible in the magnetic field. Of course, they do have mass, and mainly they're there to prevent a second magnet which is maybe right here. Yeah, you have the big magnet on the bottom, the small magnet on top, so that's kind of a reasonable picture. Okay. What forces are acting on the small magnet? Can you draw me a set of forces that are acting on the small magnet? You do it on your picture, but then it's abstracted. You set a pointed X, called a free body diagram. Okay, we are out of time, so let's do this kind of quickly. We have force acting down. I'll label that F sub mag, MAG, magnetic force. And other force. Because this magnet isn't accelerating. That'll be equal opposite to the first. I'm going to say that F compression. Okay, now that's maybe not a good label, but it's the compression of the dominoes. You're actually compressing those dominoes and they want to spring back. Now, dominoes are pretty strong, they can support a lot of weight, so you know, the weight of that little magnet there, if it's sitting on top of the dominoes, isn't going to compress it much. And of course, now if you're lowering the dominoes, then the two forces are magnetic force, whatever force the fingers are producing, right? And that's a different kind of force, there's friction involved and all kinds of stuff. The forces can get pretty complicated. But right there's just another example that you should understand intuitively as you had your hands on it and everything else. And you're going to see additional examples. You've already seen some in the assignment. Okay. So there we have it.